Okay, this is our Math 2460 Calculus 2 Zoom session for Friday, October 16th. Appreciate y'all coming out this morning. Do y'all have any questions? Anything you wanted to see?
I was mostly hoping, could we just do examples of the series and then the 9.2? I don't remember the name of it.
Okay, so basically just a short introduction to 9.1 and 9.2 and then maybe some examples.
Yeah, sure, that works.
Okay. Yeah, this is chapter 9. We kind of warned you about it. It really is kind of completely different from everything else we do. 9.1 or chapter 9, really totally chapter 9. Chapter 9 is about infinite series. Now that that word may or may not be familiar to you, but basically you can think sums. And so it really is kind of from out of left field. Why are we interested in infinite sums? What do they do for you, and etc. Here. They try to give you some examples, but I'm not sure, how well I can explain all these things. It's best way to kind of explain it with something you're probably familiar with. Y'all go to the movies, right?
Not anymore, but yeah.
Okay, you have been to the movies, right?
Yeah.
Okay. Well, I'm sure you've heard little abbreviation CGI.
Yeah.
Computer graphics. Okay. Very first movie that came out that I can remember about this was the very first Jurassic Park. Can you spell Jurassic? Have y'all seen the original Jurassic Park?
That's my favorite movie.
It is. Okay. Well, though, the whole thing was about how, Michael Crichton, I guess, wrote the book and Steven Spielberg made the movie. And in the course of them making the movie, it was about a dinosaur park where you could go and like a normal zoo, but you see dinosaurs. Now, the dinosaurs in that movie were generated from computer graphics. I'm sure you're aware of this, right?
Yeah, most of them were.
Most of them were. They did have some animatronics where they made models and the like, but a lot of them were created from computer graphics. Well, that means that although it looks on the screen like a very realistic dinosaur, it really is nothing but ones and zeros in a computer. And those ones and zeros were generated from infinite sums. For example, a sum like this, n equals 1. This is called a sigma. Here's the main notation you're going to see. It's called a sigma of, say, n. And what they mean is to plug in n. And by the way, we're going to use n for integers. And they mean to plug in 1 and then add, you plug in 2, and you use whole numbers. This is called the index. And you Add 1 to the index, so this is the n equal 1 term, to the n equal 2 term, plus 3, plus 4, plus 5, and this goes on to infinity. Forever. Okay. Well, can you tell this is going to give an infinite sum? It's going to give an infinite sum. And therefore we say it diverges. All right. Well, something like this wouldn't be used to generate a computer dinosaur. There are cases where you get finite sums, where you get finite sums. And they figured out it was actually started in the 80s. There was, you can draw a picture based on how these sums go. You can generate realistic pictures. In a computer and eventually project them onto a screen and eventually make movies from them. Y'all think of any other, you got any other favorite movies that use a lot of CGI?
Avatar.
Avatar, okay. You ever see the movie 300? That was the one with all the Spartans.
Most of the people were CGI in there, wasn't it?
No, the people weren't CGI, but the backgrounds of the battle were CGI. Now, there may have been some monsters in CGI. I think they had a rhinoceros and something else that were probably CGI. But that was the one with all the martial rhetoric. Spartans, we're gonna fight to the death. I don't know if you guys ever saw it or not. It's been out for a while. But yeah, this chapter is about the math, where you can generate, based on how these sums go, you can generate pictures, color pixels on the computer screen, and generate ultimately movie scenes and the like. Now, I can't in this chapter show you exactly how that's done. Number one, I don't know. Number two, it would be way too complicated. There's entire computer graduate programs in doing this. It's really amazing in Jurassic Park that they were given the state of computer technology back then that they were able to do that. It still holds up. It looks a lot better than even more modern movies on the CGI. It really is amazing what they did with that. The very first guy who did this, where this started, was actually down at Georgia Tech. It was a guy named Michael Barnsley. He was a professor at Tech, and he was researching these sums and trying to color pictures. And he actually created, it's called the Barnsley Fern. And they used to talk about it in the book, but it's gotten so old, they've dropped it. They did have a section, but if you've ever heard of fractals, he generated the first fractal pictures, and one of them was a fern. And the computer technology was so slow back then, he would write his code, and he didn't know what he was going to get, but he let it run all night. And he'd either come back in the next day, get errors, in which case he'd try to debug it and fix it. And when it actually worked, it took all night to generate a fern, a realistic fern. Now, with modern computers, that fern just pops up in an instant. It's really amazing how things have progressed. But you can go from a fern to generating groups of fern to generating entire backdrops. I don't know if any of that helped or not. Any questions?
Nope.
Okay. So what happens is before we can get into these sums, we've got to go to 9.1. 9.1 is actually about something called sequences. And sequences are lists of terms. Okay, and so that's where they start. And it's really pretty straightforward. Notice we're using n. X is used for continuous variables. Point this out. When we use what you're used to, f of x, say is x squared, that's a continuous variable. You can graph it. You probably know it's a standard parabola. Your domain minus infinity to infinity. But when I go f of n is, say, n squared, n is called discrete. This is really the beginnings of discrete math. Discrete, meaning n is an integer. So what I'm really doing for n is 0, I'm getting the origin. N is 1, 1 squared is 1. I'm really getting dots. So I'm up to 1, n is 2, I'm up to 2, 3, 4. And you don't fill in the middle. And they generally don't use negatives either. And you don't fill in between. That would imply you can use a half, you know, fractions or decimals in between. And you're not using this. N is an integer only. Right, but it's really the same idea. I don't know. Let's see. They'll just have you start off by listing terms. You look at example 1, they'll have you list terms of a sequence. Part A, they write it out, an, put it in braces, 3 plus a minus 1 to an n. Where I'm getting this. You can see this gibberish. So they say, well, they don't really say how many terms. But say n equals 1, and you literally plug, that would be the A1 term, plugging in n is 1, and you'd get 3 plus minus 1 to the 1. Well, minus 1 to the 1 is a negative 1, so 3 and negative 1 give you a 2. If I do the n equal 2 term, I get A2. 3 plus a minus 1 squared. I put a 2 up there for the power. Well, that's a positive 1. 3 plus 1 is 4. Are we losing anybody?
Nope.
N is 3, you get A3, and you get 3 plus a minus 1 to the third, and you're just like back to here. An odd power on this is going to make this negative, subtracting 1 from 3, giving you the 2 again. N is 4, you get 3 plus a minus 1 to the fourth, and even power makes this positive, adding to the 3, giving you the 4. It's just going to bounce between 2 and 4. You can graph, we don't generally graph these, but if you did want to, you'd have, you'd down here 1, 2, 3, and 4. 1, 2, at the 1 term you get 2, at 3 you get 2, and at 2 you get 4. I'm sorry, 2 you get 4 there, not this piece. All right, again, you don't connect in between them. And this just goes on forever. And this diverges. You just bounce back and forth between 2 and 4. They're going to be very interested whether these things converge. If it converges, it goes to a single finite number. And since this just bounces back and forth, it diverges.
So something that would converge would just be like 4, 4, 4, 4 for the rest?
Yeah. If you somehow had a formula that gave you 4, 4, 4, 4, we'd say it converged to 4. Exactly. Okay, so then the limit of a sequence, you're going to find convergence and divergence by finding limits of the sequence. So that's what they do here. Next page. Definition of the limit of a sequence. limit as n goes to infinity of an is L, the limit value. It's a lot of gibberish here, but if it converges, L is finite. And if L is infinite, limit does not exist, it's infinite in effect, the sequence diverges. So the limit of a sequence is limit, n goes to infinity of your terms, L. L finite converges, sequence converges, L infinite, sequence diverges. Okay, there is a lot of stuff here that the limits work exactly like limits for Calc 1. I don't know if I need to copy any of this down. Trying to get to some examples, but if we have a limit of an AN is L and a limit of the BN is K, if you take a multiple of it, you can put numbers in and out. You can add or subtract. You get the sum or difference of the limit values. You can take a product of the limits and you get a product of L and K, and you can take a quotient. You get the quotient of the limits. And so actually by example 3, which is what we did with example 1, now they're trying to find you if you diverge. Since it alternates between 2 and 4, your limit does not exist, so you diverge. They have a whole bunch of other stuff called squeeze theorems and the like that I usually don't get into. We try to treat this very lightly, which can be very vague. So why don't we try a few examples out of what we've talked about. We don't worry about monotonic and everything. So I don't know if anybody tried the homework. I know I canceled the first Zoom meeting of the week. I don't know if any of y'all try. Any of y'all try any of these? Have trouble with any of them?
I really haven't touched it yet, no.
Okay. Do you want to see something? See, they're giving you a little formula for them, and they want you to write the first 5 terms. Does anybody want to, you want to see one of these?
Wait, so like you would just, for like, let's say number 5, is that 3 raised to the n?
That is
right?
correct.
So would it just be 3, 9, whatever, 3 raised to, yeah, would it just be like that?
Exactly.
Is that what it's asking?
That's all it's asking for. This is almost so easy, it's hard. Yeah, so page 596, number 5, just to write that out. Your AN is 3 to the n, and they say list the first 5 terms. So literally, I'll write it out real. You almost do it in your head once you see it done, but I'll just write it out really obvious. Yeah, so I go A1 is the first term, that's 3 to the 1, that would be 3. Second term is A2, 3 squared, that would be 9. A3 would be 3 to the 3rd, that's 27. A4 would be 3 to the 4th, that would be 81. You might need a calculator to do 3 to the 5th, or 81 times 3. That'd be 243. Now, you can leave this like this, that's fine for the answers. The book may list it in a brace form. 3, 9, 20, 27, 81, 243. Either one is fine. But yes, that's all they're asking for. Questions about that?
This feels like this feels like middle school type of stuff.
It kind of is.
Where does it get harder? Where is this?
There's 10 sections.
Oh, okay.
It gets hard. It gets harder when we start testing for convergence. And there's like 10 tests of convergence for this starts at 9.2. And there's like 10 total, but online, I boil it down to 8. And then trying to keep all that straight, that's the first half of the chapter. And then there's some strange formulas from 9.7 on to 9.10. Now, some of the hardest stuff is like in 9.8, 9.9, and then 9.10 is a repeat of 9.7. And I know that makes no sense at all till you actually see it face by face. If you've ever heard the phrase dreading something is worse than actually doing it, that kind of applies to chapter 9. Every time I charge into it, I really dread it. But once you're in it, yeah, you kind of see it. Yeah, you know, not that bad. It just is so much different than the rest of the stuff. The next kind of stuff they'll have you do is factorials. Now you may or may not, that's this exclamation point. Have y'all seen that or run into that anywhere? Or that could be out of the blue if you hadn't had any statistics.
I've never seen that.
Never seen it. Okay. Well, it turns out, I'll do it with numbers first. That a lot of the formulas in this chapter will have terms that look like this. 3 with an exclamation point. That's read 3 factorial. And what it means is that you start with the given number and you multiply by every whole number back to 1. This will work out 6. This is on your calculator. You got to really hunt for it though. I believe it's under the math menu and over to PRB for probability. And there you are, it's option 4. Now, if you just hit option 4, you get this, and who knows, answer is the number that was the previous answer, and the thing, who knows, probably just nothing but errors, yeah. So to really use this, I start with a 3, and then I hit math, go over to PRB. My fault, start again. I hit 3, math, over to PRB, and I hit option 4. And there you are, just like you'd write it on paper. Hit enter, and there's my 6. And this pattern is programmed into the calculator under that exclamation point. So if I wanted 5 factorial, just to do another number, 5 times 4 times 3 times 2 times 1. You can probably still do that in your head. 20, 60 times 2, 120, I believe. 5, again, math. You can go the other way and wind up right at PRB. It kind of circles around in option 4. And there you are. 5 factorial, 120. Okay. But in 17, they give you formulas. So if I do a generic n factorial, this means my lead number is n. So I start with that n, and I multiply by 1 less than that, 1 less than that, until I get back to 1. This is read n factorial. Any questions so far before I show you 17?
Nope.
Okay, so 17, page 596, simplify n plus 1 factorial over n minus 1 factorial. There's really no calculus at all with a lot of this stuff. That's the other strange thing. Well, giving this kind of pattern, this means you start with what's given. 1 less than that will just be an n. 1 less than that will be n minus 1. 1 less than that will be n minus 2, back to 1. Questions about that? On the bottom, you'd start, what's given is n minus 1. 1 less than that is n minus 2. 1 less than that is n minus 3. And again, you're back to 1. You'd have an n minus 3 as that piece there. You see how things cancel?
Yeah.
All the n minus 1s with all those n minus 1 back to 1. And a formula for this, a simplified formula, is n plus 1 times n. I like to check 1 on both sides just to show this isn't total hocus pocus. So give me a whole number for n, make it below 69. I think the maximum you can do a factorial on these calculators is 69. It generates very large numbers when you multiply 69 of 68 of 67 all the way back to 1. I think the maximum you can do. So below 69.
23.
23. So we use n is 23. So this gives me 23, add 1. I'll punch it with the factorial key. 23, subtract 1, factorial, divide it. And then on this side, I'll get 23, add 1 times 23. All right. So, let's see, 23, add 1. I could punch 24 factorial, math, PRB number 4. And divide by, y'all see that? Let's see, 23, subtract 1, math, PRB number 4. Okay, so there you are. Punch exactly like it's written on paper. Coming up with 552. Over on this side, I get 23, add 1 times 23. Does that prove anything to anybody or only to me?
That makes sense.
Okay. Yeah, just trying to give you some confidence in it. Okay, so further down the page, I think I jumped to 29. If I look at the assignment, let's see, assignments for this week. Well, I did 17 and 19. Okay, I just did 17 out of 19. Okay. And then I jumped to 29 to 43, actually to 37. So do you want to see finding that was this section of problems? Do you want to see an example of those?
Yeah, sure. Why not?
Okay. I'll try 29. They give you that AN is 5 over n plus 2. All right. Again, they ask these directions backwards. They want you to determine convergence or divergence. If you converge, find the limit. You actually find the limit first, and that tells you whether it converges or diverges. Okay. They ask it backwards. Okay, so what happens is, just to show you what this means, I'll write out a few terms just so it isn't total gibberish. You basically have a sequence, and if n is 1, you're at, put them in braces, n is 1, you're at 5/3. That's the n equals 1 term. If n equals 2, you're at 5/4. If n equals 3, you're at 5/5, which is 1. You see the pattern? At n equals 4, you're at 5/6. Everybody get the idea?
Yeah.
Okay. So they want you to find its limit. So you take the limit as n goes to infinity of 5 over n plus 2, which is 5 over infinity plus 2, which is 5 over infinity. And we showed you these limits, I think it was in section 8.8. Number over an infinity, everybody remember, gives
0.
0. Can you kind of tell looking at the sequence? Yeah, you're starting bigger than 1 here. You're still bigger than 1 here. You hit 1. 5, 6 is less than 1. Your next one is what, 5, 8s? No, 7s. I'm sorry, 5, 7s. You're going up by 1 on time. 5, 7s. Then you're going to what, 5, 6, 5, 8s. Can you tell this is the n equals 5th term, n equals 6th term. Can you tell your fraction's getting smaller and smaller and smaller?
Yeah.
And you're therefore approaching 0. All right, so they give you a few more there. That about finishes 9-1, and we're at 30 minutes. Do you want to see what's going on in 9-2?
Sure. I won't be able to stay for the whole time because I got to get to a class, but yeah, I can stay for the beginning.
Yeah, no problem at all. I can't see y'all's names or pictures. Does anybody else out there want to ask any questions? And I just lost my, how did that happen? Let me see if I can get back to my picture. Let's see if I can get back to the picture. Anybody else out there want to ask any questions? Okay, I got your names now. Mr. Driscoll, Mr. Gatan, Mr. Iverson, Ms. Drummond, Ms. Brown. Anybody want to ask anything? I'll see if I can get my camera back.
I don't think we have any questions.
Okay. Feel free to chime in. If I can get this camera back. All right, hopefully we're back. So 9-2 is your infinite series. This means infinite sums. And again, the whole chapter, the rest through 9-6 anyway, is about tests for whether these infinite sums will converge and be finite, or diverge and be infinite. Okay, let me, if we were in the regular classroom, I have kind of a demo. I don't know if y'all can imagine sitting in a room, your classroom, and you're sitting at a desk, and here's your door. All right. And so I ask you to leave through the door. Well, imagine we've got a wise guy, and he stands up and he says, I can't leave. And I go, why? And he goes, well, because I can move halfway there and stop. And then move halfway again and stop. And halfway again and stop. And if I keep subdividing halfway there, I'll never get to the door and leave. Yet we all know that you can just walk right out the door. So yes, you can infinitely subdivide it and add up the pieces, but the pieces will add to the distance to the door. Another example of this is, let's say you go to Thanksgiving and you go to grandma's house and she has her delicious pie and she sets it in front of you and you sit there and you go, you know, I could never eat all this pie because I could eat half of it. And then I could eat half of that at the next meal, and I could eat half of that at the next meal, and I could eat half of that at the next meal, and half of that at the next meal. And doggone, I get all these infinite pieces. And I could never eat all of grandma's delicious pie. Y'all ever think like this? Probably not. It's only math.
All the time.
All the time, yes. Okay. Yeah, we all know you could sit down and you could scarf down grandma's pie in one sitting. So all these infinite pieces add to a finite sum, the whole pie. So they try to show you this. So I can get to some examples to try to condense this as much as I can. They're back to the summation notation. So an infinite sum of n equals 1 to infinity of an an, and we'll just generically write out pieces. A1 plus A2 plus A4. Okay, goes forever. Again, it's the conditions, the whole subject, the whole chapter are the conditions where this will be finite and converge, and when it will be infinite and diverge. So to find a sum, we form partial sums. So we start with S1 is A1, and that's what they're doing right here. S2 is the sum of the first two terms. S3, the sum of the first three terms. S2, A1 plus A2. Third partial sum, each of these individually are finite. You just take the first three terms. S4, the first four terms individually. And you form a sequence. Try to keep it in view. Form, sequence. You call it S in. So you list S1, S2, S3, S4 out as far as you can go, infinitely. Okay, so the nth partial sum is A1 plus A2 plus A3, all the way out to the nth term. That's what they're showing you here. All right, does it not make sense if you take the limit as n goes to infinity of that Sn and you get an L finite, meaning you take a limit of all these things and you get the nth term and you get a finite result on that limit, then your series, summation n equals 1 to infinity of your an, converges. And this L is the sum of the series. They're using the letter S in the book. The series. But if your limit is n goes to infinity of your Sn, meaning your sums go off to infinity, they just add up to infinitely larger and larger, your series sum n equals 1 to infinity of an diverges. All right, let's pause here for station identification. Does this make any sense at all, or is this kind of complete gibberish?
No, I think it makes sense.
Okay. That's why you do sequences in 9-1 first, so that we can use them to form partial sums and take limits of the sequence and see if our sums will be finite or infinite. All right, let me run to, well, while we're here, let me run to some homework, do a quick homework example, because it probably is gibberish without seeing some numbers. And then I need to go back and show you, there are a few of these that have actual formal names that are extremely important, like the geometric. Okay. But let me do an example of this while we've got this here. This is where the homework starts. And then we'll go back through and show you some of the name series like geometric and the like. All right, so if you go to the homework, page 605, it starts, say, with number 5. And so they give you a sequence like this. I'm sorry, it's not a sequence, a series like this. They want you to list these first 5 partial sums. Once you see it done, you realize it's not hard, just arithmetic. So you're given 1 plus a quarter, a ninth plus 1/16 plus 1 over 25. It says list or find the sequence of partials S1, S2, S4, and S5. Well, S1 is really simple. That's just 1, very first one. S2, you have A1 plus A2 is the sum of the first 2. That'd be 1 plus a quarter. You could probably do that in your head. 4/4 plus 1/4, that'd be 5/4. S3 would be the sum of the first 3. 1/4 plus 1/9. Now, do you see I don't really have to reinvent the wheel? I've already done the first 2 here. I really only have to take the previous sum and add the next piece. Everybody see that? Add 1/9.
Yeah.
Okay, now this is a little nastier fraction problem. The book actually just reports it as decimals. I checked the answer in the back of the book and it just reports it as decimals. So instead of wasting your time working out the fractions, we'll just run to a calculator, 5/4 and add 1/9. They're getting 1.3611. When I do the next one, I only have to take, so you got these first 3 and I'm getting 1.3611 and I'm adding 1/16. Because I've got the sum of the first 3 adding on the 4th one. So I can add on 1 divided by 16, 1.4236. And finally, for the 5th one, you start with that one, because that's the sum of the first 4, 4/2, and add on 1 over 25. 1 over 25. I just add on 1 divided by 25, 1.4636. That's really all there is to it. That's all they want between 1 and 9, or I'm sorry, 5 and 10 there. My son launched a meeting. Oh, every time he does that, he messes up. Okay, let's see if I can get the camera back.
I personally actually have to get going, so thank you.
Well, absolutely, no problem.
Have a good one.
Yes, thank you for coming out. Okay, trying to get the camera back. All right, we're back. Had pretty good Wi-Fi. I remember one meeting, I don't know if it was last week or the week before, we had very lousy Wi-Fi, kept freezing. Hey, I better keep my mouth shut. I'll jinx it. Everybody left. Y'all want to see more? There's more details we're going to quiz you about on the quiz that's available today. Do y'all want to see those details or?
Yeah, that sounds good.
Okay. Well, we'll go to a geometric. This is extremely important. This is one of the very few that you can actually find a sum for. 601 geometric. And it goes as a sum, and they start this one at 0 to infinity of a r to the n. I'll write it out. A, because n is 0, your r to the 0 would be 1. You just get an a plus a r to the 1. I'll use the r, I'll just to show you all the pieces, plus a plus, I'm sorry, that's a plus ar squared, ar cubed. I'm not doing well. Okay, and this goes forever. All right. R to the 0 is 1, so that's an a, plus an a, r to the 1 is just r, ar squared, ar cubed. Okay. Now, you probably think you've never seen anything like this before in your life. You couldn't be more wrong. It's basically your standard polynomial. They just, for some reason, like to use r instead of x and a instead of a number, but you know, it's exactly like something like this with an a of 1 and your r equal to x. But it just goes forever. It's nothing really but your standard polynomial. Now, I'm not going to derive this just online. Don't have enough time if I want to get to some examples. But this has a finite sum if the r is less than 1. Can you tell that? You'd have a plus a, let's say a half, plus a half squared. I'll use r as a half, number less than 1. This is getting smaller and smaller and smaller. And the finite sum turns out is a over 1 minus r. And they show that to you at the bottom. R less than 1. But it diverges. R greater than or equal to 1. Can you tell that? Let's say r is 2. You'd have a plus a times 2 plus a times 2 squared plus a times 2 cubed. You're just getting bigger. You're getting 2a plus 4a plus 8a, whatever the a is, you're just getting bigger and bigger. Same thing with 1, you're just getting bigger and bigger. But if you go with a fraction, you get smaller and smaller. When you square fractions, cube them, except they get smaller and smaller and smaller. And it turns out it'll go to this sum. Are we ready for a homework on that?
I think so.
Okay. Try problem 29. We're doing a sum of n equals 0 to infinity of 5 times 2/3 to the n. I'll write it out just so you, that's the biggest thing. This looks like gibberish. So a lot of people don't know what they mean. Well, they mean 5 times 2/3 to the 0 plus 5 times 2/3 to the 1 plus 5 times 2/3 squared plus 5 times 2/3 cubed, and so on. So you're really getting 5 because 2/3 to the 0 is still 1, so it's a plain 5 plus golly, plus 5 times 2/3 plus times 2/3 squared, 5 times 2/3 cubed. We could run some number, decimals out and show how this is getting small. Maybe I'll just run a term here. 5 times 2/3 cubed, 2/3 to the third. You're at 1.48, and you started at 5. So you see how your terms get much smaller and smaller? 5 times 2/3 cubed, you're down to 1.48. You started at 5. All right, to find the sum, you just got to find what your A and R are. So you have sum of n equals 0 to infinity of 5 2/3 to the n, matched to n equals 0 to infinity of a r to the n. Can you tell your A is 5 and your R is 2/3? Is that obvious or only obvious to me?
I don't understand that.
Meaning your sum then is plug and chug is A over 1 minus R. So that's 5 over 1 minus 2/3. Now you can punch that out as is. I don't know if you want to work it out by hand. 5, 1 minus 2/3 is 1/3. That's 5 times the flip is 3 over 1, and you get 15. Turns out this will add to 15. You can program it on a computer to take out a whole bunch of terms, and the more terms you take out, the closer and closer you get to 15. If you want to see this, I'll just punch out a few just to 5 plus 5 times 2/3 plus 5 times 2/3 squared plus 5 2/3 to the third. Let's see how close we get. Enter. Well, we're up to 12.0. By here, we're at 12.037. We're working our way to 15. I don't know if that gives you any more confidence in it or if it's still all gibberish, but there's one more little topic I need to cover. Any questions about this, or y'all got the patience for it?
I think we're good on that.
Okay. It's our first test for convergence. It's actually a test for divergence. It's a very simple one. It's this nth term test for divergence. Call this number 1. It's the nth term test for divergence. Actually show it down. It's actually down here. It's actually this right down here. If a limit as n goes to infinity of an a(n) is not equal 0, then a summation of n equals 1 to infinity of a(n) diverges. It probably reads like pure gibberish, but it's actually the simplest thing in the world. Okay. Let's say I get, just for example, I take limit as n goes to infinity, I'm off my screen, of a(n), and I get 3. All right, you understand that that means my summation then of n equal 1 to infinity, I can have a bunch of terms at the start, but at infinity, my terms are 3. So I'm coming out here, and then when I get toward infinity, I wind up adding 3 forever. And you see, you just get bigger and bigger and bigger. And you diverge. But be careful, just because the limit of your terms equals 0 does not mean you converge. You were thinking, well, I would add 0 forever, so I'm fine. No, they may not go to 0 strong enough. That's where this stuff gets really tricky. Let me show you how this is used. Page 605. Try problem 13. They're telling you that it's diverging, and they want you to come up with the argument. Okay. So you take summation n equals 1 to infinity of n over n plus 1. Verify that it diverges. So I try this, generically we call it the nth term test. Limit as n goes to infinity of n over n plus 1. You see you get infinity over infinity plugging in? And now we reach all the way back to the very first section of the class. Y'all remember L'Hopital's rule?
Slightly.
Okay. You can take the derivative of the top and the derivative of the bottom and take the limit again. Limit as n goes to infinity, derivative of your top is 1, derivative of your bottom is also 1. There's no n to plug in, so this is equal to 1. You understand that this means that on the sum, I will wind up adding, blah, 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 adding stuff. But at the very end, I will add 1 forever because the terms at infinity are 1. So this diverges by the nth term test for divergence. Questions about that? You can almost see it by writing out the terms. I don't know if this will help or not. If you write out the terms, summation n equals 1 to infinity over n plus 1, we'd have 1 over 1 plus 1. That'd be 1/2. 1/2 plus 1 over 2 plus 1/3 plus, I'm sorry, that's 2/3 plus 3/4, right? 3 over 3 plus 1, 3 over 3 plus 1. This is 2 over 2 plus 1. Plus you'd be 4/5. You see what the terms are going to? So you're at 0.75 there, you're at 0.8. You see what the terms are trending to what?
Is it 1?
1. You're at 5, what, 6, right? 6/7. Your terms are not going to 0. The terms are trending to 1. So yeah, you're going to get to 1 out to infinite terms, and you're just going to add 1 forever. That's all it's saying. Questions about that? Let me show you problem 11, because it doesn't use the same test. Summation n equals 0 of 5 times 5 halves to the n. Verify. It's off page 605. Oh, we're about an hour. This diverges. Well, you should recognize a geometric. Summation of A and R to the n. Okay, can you tell your R equals 5 halves? And that's greater than 1. You could call this the geometric series test. This diverges because is geometric with R greater than 1. That's really all you got to say. This is as close to proofs as you're going to get in this class. If you compare this to 19, summation n equals 0 to infinity of 5, 6 to the n, they want you to verify that it converges. $19 right here. Well, you recognize this is geometric. Can you tell the A is 1 and the R is 5, 6? That's less than 1, so it converges. Because it is geometric with R less than 1. Questions about this? Does anybody have any stomach for any more, or have we opened up your heads important enough today? Everybody is so awestruck you can't speak.
I think it's pretty straightforward. I don't have any questions.
Okay. Quiz 7 is available. It's been posted. Made it due Sunday. Yeah, we got a long chapter. It'd be a while for the test on chapter 9. We've got 8 more sections to go and many more tests of convergence. So individually, maybe you don't think this is very hard, and maybe it isn't, but trying to keep the entire chapter straight by the end, a lot of people have found a little overwhelming. But again, you just got to go at it piece by piece. Does anybody want to see anything more, or are we ready? We're a little over an hour. Are we ready to end?
I actually have to go somewhere else after this. I have a doctor's appointment, so I don't have time to continue on. I don't know about the others though.
Okay. If anybody wants to see anything else, speak up. Otherwise, I'm going to go ahead and end the meeting. Y'all want to see anything more? All right, I guess hearing nothing, we'll go ahead and end the meeting, and we'll be back to the regular Zoom schedule next week. Appreciate y'all coming out early on a Friday morning, and hope y'all have a good rest of the weekend.
You too. Thank you.
Sure thing.